I know it's been a while since I put a video out. That's because I'm back here in Pakistan for a while with the other workshop. This is where I have my Colchester Student lathe. I thought today I would do a little exercise using the taper turning attachment. I need to produce a number 3 morse taper on this piece of 1 1/4 inch steel. I'm going to start by facing and centering it, setting up between centers, then we'll have a closer look at using the taper turning attachment. Just a few words on my setup for turning between centers. This is the sleeve that comes with the Colchester Student, and it fits in the internal taper here, and it gives me a number 3 morse taper here. As you can see, this was quite messed around. It had been in a box, probably with the lathe turning tools, and it generally got abused. So I did my best to clean that up, attending where possible to each individual ding to get it down to the surface, and so I did the best I could with that. And similarly with the internal taper, and I actually made a little tool that goes inside there for scraping inside, and I did the best I could there. That's actually the subject of one of my other videos on renovating this lathe, if you want to look at that. And having cleaned this up and got the best result I could by hand, I tested it all, measured it, and then I put a scribed mark, a radial mark there, which lines up with the keyway so that I can get repeatability. So we'll put that in, and then I've got my soft center here, which previously I've turned down, and we'll put that in, and we'll see how repeatable this is. Okay, you can see there the run out, it's around about half a thou on the center, the soft center there, and that center I turned before. I don't need to return that, that's perfectly adequate for this job. Time to set up the taper turning attachment. So the first thing we need to do is put the clamp on the bed. I normally keep this out of the way. If this is missing on your machine, then I have an earlier video you might like to look at with a drawing which gives some of the critical dimensions. This fits on the back of the bed, and we engage it with the drawbar. This clamps down. There's an eccentric wheel here which provides a slight degree of adjustment in the vertical height there, to make sure there's no fight between the 2 halves of the assembly. And once that's zeroed out, then we can lock the set screws. I added these because I wanted to minimize any backlash in the assembly. You'll see why later. And then there's a clamp on the rear. So now we're set up, and you can see at the rear there the taper turning attachment in operation. And if you wanted to perform the same taper turning attachment operation further up the bed, then we can just slide the whole thing along and lock it again. So here's a diagrammatic representation of the taper turning attachment on the Colchester Student. Here you see the bedways shown in yellow, the saddle in green, the cross slide in red, and then the taper turning attachment which locates on the rear of the saddle. At the bottom of the attachment is the lower slide, and that slides in a housing on the rear of the saddle. And on top of the lower slide is the upper slide, which can rotate, and that is what generates the taper. The cross-slide lead screw bearings are actually housed on top of a slider which sits on top of the upper slide, and the clamp restrains the lower slide. So we can see what happens when the attachment is in use and the saddle is traversed. So as the saddle is traversed, you see the slipper block moves along the top slide, and that causes the cross slide to move, and the same in reverse. Now, one of the beauties of this design is you can move the cross slide independently, as seen here, and then if you disconnect or unclamp the clamp which is further down the bed, then the whole assembly moves like that, which means that the taper turning attachment is effectively disabled. So it's very quick and easy to engage, and the beauty of this is you can leave the taper turning attachment at a setting that you may want to use again in the future without upsetting the other capabilities of the lathe. So I've drawn up what we need to turn. I've got here a spigot on the end here which engages with the ejector mechanism to eject it from the tailstock quill. Got a critical dimension here of 0.783 and a reference diameter here of 0.94 and a reference length of 3.123, and that corresponds to a half angle of 1.437 degrees. So what we need to do now is set up the taper turning attachment, and to do that I need some measurements here. What I'm going to use is the tailstock quill and a DTI off the cross slide, and then look for a movement in the DTI over a specified length. So the reference length I'm going for is 2 inches. So a little bit of trigonometry there tells me that for an angle of 1.437 degrees, I'm going to find 50 thou of deflection. That's what I'm going to look for. So we'll go over to the lathe and we'll set up the taper turning attachment to achieve that deflection and so the right angle. Now hopefully you can see the setup we've got here. We've got the tailstock quill out about 2.5 inches. Then the DTI is on the cross slide, and the cross slide of course moves with the taper turning attachment, which you can see is already set over at the back there. So we're going to traverse the saddle using with the taper turning attachment engaged, and then we're going to detect the deflection on the DTI over a distance of 2 inches. So I've set the top part of the taper turning attachment approximately at the angle I think it should be. These two clamps here are released, and this top slide rotates relative to the bottom one. You can see here the clamp at one end of the taper turning attachment and at the other end. So I've released those and then rotated the top slide until I got the desired angle. The cross slide thrust bearings are actually mounted on top of this block here relative to this slide. So you can move the cross slide independently like this, which is nice, and so you can easily put a cut on and return to wherever you were before, or even do other machining operations. If you just undo this, then you can keep this set up at the right angle. So what we're going to do now is zoom in and work on getting this angle right using the DTI. So the question is how to get a reasonably accurate length of traverse of the saddle and the DTI along the quill here. And the way I elected to do it was to engage the lead screw with a known TPI and then count off the rotations on the headstock. And that will give me a fairly precise 2 inches of traverse of the DTI. So we'll do that. One, 2, 3, 23, 33. Okay, that gives me my 2 inches of traverse, and we were looking for 50 thou of deflection, and we've got 45, so we need to adjust that taper slightly. Now I do the same thing in reverse, so you need to go slightly beyond and then come back and make sure that all the backlash is removed from the mechanism. So we'll move forward a bit further. And then we'll reverse, come back to 0 position. And then we're ready to go back in the other direction. And I get a 0 on 50 thou. Come back again. 1, 2. Okay, and that's showing 52.5 thou deflection. Yeah, I think in the forward direction I probably didn't take up all the backlash. So we will try that again. And I'll change the angle so we can look from above and see what's happening at the DTI. Okay, we'll start by winding the saddle back to the far end of the quill. And just engaging the lead screw, and then we'll take a couple of turns to take out all the backlash in the system. And then we'll wind the cross slide into 50 thou on the DTI, and then all we need to do now is count 24 revolutions of the headstock in reverse direction. 1, 2, 11, 12, 13, 33. 24. And you can see that the DTI is showing 0. Let's just move that around a little bit so you can see square. Yeah, quite close to 0. There we are. So that's the taper turning setup ready. So we can now put the bar between centers, rough it out, and then cut the taper. We've already seen how the taper turning attachment works, and I think that's very clear. But there are some issues that you need to bear in mind when actually using the machine in practice. These have to do with backlash in the mechanism, and there are quite a few sources of potential backlash. You have potential slackness in the thrust bearings, which are housed, in my case, in the sliding block. You have almost certainly some backlash between your lead screw and the nut. Then you could actually have some backlash in the clamping mechanism, and I mentioned earlier I tried to minimize that as far as possible. You could have some rotation in your saddle if it's a worn lathe. To a lesser extent there could be some lateral movement in the lower sliding member, and also between the upper sliding member and that sliding block. All these conspire together to cause backlash. And why is that important? Let's take the case of turning from a smaller diameter to a larger diameter, from the tailstock to the headstock. And we can plot the cross-slide travel against saddle travel, and that will give us some way of understanding what's happening with the backlash. So we're ready now to use the taper turning attachment, and we're starting at 0 with all the backlash taken up. And as soon as the saddle moves towards the headstock, either under power or by hand, the taper turning attachment will move the saddle and will produce this, this line. And we need to start before the taper and finish after the taper so we don't have any steps or interrupted cuts. At the end of the cut, the saddle will be moved towards the tailstock, and there'll be a period of dwell when the cross slide does nothing, and then eventually it will start to move inwards again. Now once we have gone sufficiently rearwards to ensure that the cross slide has moved inwards far enough, then we can put on a new cut. Then as the saddle moves towards the headstock, again there'll be a period of dwell as slack is taken up, and then the new cut will ensue. So that's probably the easiest way to use the taper turning attachment. And that requires that there is space on the right hand side there at the smaller end of the taper to have this excess travel of the saddle to take up any slack. But what happens if we don't have that? If we have a setup like this? Then we need to consider an alternative approach. So one way of doing that is to start from the larger diameter and move to the smaller diameter. And if we plot the tool paths, then we can see what happens. So we start at the larger diameter, and again we zero the cross slide dial. The taper turning attachment moves the cross slide inwards as the saddle moves towards the tailstock. And again, you need to start before and finish after the actual length of taper. And then at the end of the cut, you withdraw the cross slide as you would if you were screw cutting, and then move the saddle back towards the headstock, and there'll be a period of dwell when the cross slide doesn't move, and then slack will be taken up, the cross slide will move outwards. And then at the end of that movement, you need to return the cross slide to the 0 position, add your depth of cut, and then move the saddle towards the tailstock. Again, a small period of dwell, and then the new cut will take place. So that's fairly straightforward, and that enables you to operate with less space. Now, you need to be aware that machining from the large diameter to small diameter, there is the possibility of a foul up. So let's see what happens if you don't withdraw the cross slide at the end of the cut. So starting from the beginning, taper turning is underway. You fully traverse the length of taper, and then just suppose that you don't withdraw the cross slide, but you return the saddle to the tailstock. You're going to get a dig in, and if you keep going, you're going to get a cut, but it will be of indeterminate depth, and that may take you below your size, or it may be just a too deep a cut, but the point is it's not very satisfactory. So that's why you need to withdraw the cross slide at the end of the cut. Now let's just compare the two setups there, the advantages and disadvantages. First of all, from small to large, it's simpler, there are fewer settings, but there is a danger of indeterminate cut. And I didn't mention this before, but you could find that because the cutting force is outwards, and also the cross slide is being moved outwards, it's not clear whether the cutting forces are pushing the slide out or the taper turning attachment, so you might get steps and ridges. So looking at the large to small, in that case you can get into smaller spaces, and also you don't have this problem with indeterminate depth of cut. So that's the approach I'm going to use in this little project, and we'll see how it works out. As I'm doing the plane turning at the moment, we don't need the taper turning attachment, so I just disconnected the clamp on the end here, so that's disconnected. So that means that the taper turning attachment's not operational, but everything else on the lathe works as normal. Of course, when you don't have a live center, you've got to make sure you keep the lubrication fresh on the tailstock center there. Out now, including the spigot on the end here. So I just need to finish this. I've got 40 thou to come off the diameter. I've just touched up the tool, and we're ready for some finishing cuts before we embark on the taper turning. I'm just going to turn a reference diameter on here so that after I've machined the taper and I put it in the headstock, I can then check this for run out. At last, get to do the taper turning. As so often is the case with machining, it's 95% setup and 5% actually doing the job. Anyway, we're ahead now. We're getting into the taper turning, moving from the larger diameter to the smaller diameter. So following the pattern which I showed in the diagrams, at the end of the cut we're drawing the cross slide, returning the carriage, resetting the cross slide to 0, adding a small cut, and then engaging feed, making sure that you start before the taper. Okay, just checking the small diameter, reference diameter, see how we're going, and then I'll 0 the cross slide at that point, and then we will know how much further we've got to take off the diameter. At this point the center is getting a bit hot, despite frequent application of lubricant. I really do need to get a rotating center, live center, but good ones are expensive and I don't want to buy a cheap one. So we've still got about 1.2 millimeters or just under 50 thou to take off the diameter, so now is a good time to try this in the tailstock. I've put some marking blue on here and we'll just give that a test and we'll see how we're doing with the taper angle. I made a small adjustment to the angle just to make it slightly steeper. It was touching slightly at this end, so made that adjustment. Hopefully I can move towards the final cuts now. So I've tested this again with blue, and that's a better result. I think my angle actually wasn't set correctly, even according to the tailstock's quill. So it's around about 1 thou smaller over the 2-inch difference, over the 2-inch length as compared with before. But that's definitely a better fit, and I think now we can proceed to the final cut. Once I got into the swing of things, it was really like screw cutting, except a lot faster. Yep, we're on size there, so I'm happy with that. We'll take this out now and we'll do one final test in the tailstock. Yep, I'm happy with that. It's probably a bit difficult to see on camera, but the other slight problem here, as I mentioned before, is this mark here. There is a high spot on the inside of this taper, which is probably another project. I'm going to have to see if I can find a way to eliminate that. Okay, that's this project complete. Maybe there's been something here which has been of interest, or maybe new, or maybe you're a more experienced machinist and you've got some suggestions. So whatever, I'd love to hear from you. And again, as always, if you appreciate this video, do give me a thumbs up and consider subscribing. Hopefully next time I'll see you back in the UK.